10 o'clock, so.
All right, so welcome back to the last day of AlCoVR. We will be not in VR this morning, but we will in the last social gathering at 2 o'clock Eastern. So yeah, Bruce is going to finish up with the last day of lectures on dynamical algebraic combinatorics. Take it away.
Okay, thanks so much, Maria. So I think you all know what we're going to do today. We're going to prove those equivariances between those three different sets or three different pairs that we stated at the end of the last lecture. Of course, we only need to prove two equivariances because equivariance is an equivalence relation, so we get the last one by transitivity. And so here's the first one we're going to work on. That's going to be, let me see if I can, there we go. We're going to show that rotation on bit strings is equivariant. Let's see with promotion on linear extensions of a disjoint union of an M-element chain and an N-element chain. Okay, and try not to write on the board if you can. I know it's hard, but, oh, and don't raise your hand. I would suggest just unmute because I can't see the chat. So just go right ahead and say something. That'll be the best thing.
Great, thanks, Bruce.
Okay. So so here's where toggles are going to really come into play, because remember, promotion was defined in terms of toggles. So we'd like to define rotation in terms of toggles, and that turns out to be surprisingly easy to do. So we're going to define the rotation toggles so Ri is going to be from the bit strings B and K to the bit strings B and K. And it's kind of the simplest possible thing you could do. If I want doing the ith rotation on the bit string B1 through, say, BI plus 1, Bn, just exchanges those two bits. Okay, so let's do a quick example, make sure we're all on the same page. What if I did R2 on the bit string 11001? So that's going to try exchange the second and the third bit, which is going to give me just 10101. Okay, everybody see? Any questions? Good. What if I did R3 on that same bit string? Well, now I would try to exchange the third and the fourth bit. And of course, that doesn't do anything because both bits are 0. So essentially leaves it invariant. Or you can think of exchanging the two bits, but the two bits are equal. Okay. So important thing, a way to think about this, which will make it more like what we did in promotion, is that Ri of a bit string, it switches a 1 and a 0 if the two-bit string, the two elements we're interested in are 0, 1 or 1, 0. And it leaves it invariant if these two have equal entries. So let's recall and compare this with what my SI, right? The SIs for promotion, what those did. So So we had these SI toggles from linear extensions to linear extensions. And they were defined by saying that if I took a linear extension, that either switched the two if I stayed within linear extension land, right? So if this was a linear extension, and otherwise it just left it alone. So these, right, this is starting to look very similar now. And remember that promotion was just defined by taking the composition S1, S2 back to Sn minus 1. Oh, thank you so much. And now my phone wants to go off.
No problem. Yeah, I there were a lot of floating cursors, and I finally found the setting that turns that off.
Yes, I tried to do that this morning and couldn't, so I'm super glad you did.
There we go. Yep.
Excellent. Okay, so now we've got the setup, but remember, for equivariance, we need a bijection between the two sets that commutes with the two operations. So we need to define the bijection, and it's kind of the simplest possible definition you could imagine. So we're going to define a bijection. I'm going to call it phi from linear extensions to the bit strings so phi of a linear extension is going to give me a bit string. And I just have to tell you what the BIs are. And they're very simple. BI, it's going to be 0 or 1, right? It's a bit string. It's going to be 0 if xi, the ith element of my linear extension, is in the first chain. And it's going to be 1 if it's in the second. You just mark which chain you're doing things in. Okay, let's do a quick example just again to make sure that this is really clear. So go back to our usual example where m and n are both 2. So, right, we have 2 disjoint union 2, which I can think of as labeling things wx, y, z. So think of this as the 0 chain, and this is the 1 chain. So therefore, if I had w, y, z, x as my extension, what would that go to? Well, w is in the 0 chain, y is in the 1 chain, z is in the 1 chain, x is in the 0 chain. That's your function. Everybody see how this works? Any questions? This is our fundamental bijection that we're going to use. Okay, well, then we're ready to prove our theorem. We've got everything in hand that we need. So motion on these linear extensions is equivariant with rotation on these bit strings via this map phi. Okay. Yeah, I'm not seeing the floating cursors. I don't know whether anybody else is.
Yeah,
Okay.
just one student was, it's fine.
Right, exactly. I think I may have, there may be one more. Oh, yes. So we need a lemma, actually, which I somehow managed to skip over. Right? I need to show that rotation is given by these toggles. Okay, so on BNK, rotation is indeed the composition of these toggles, R1, R2, up through Rn minus 1, right? Where these are the rotation toggles where you just switch the bits. Proof of this is really simple. Well, let's just see what that composition does to a bit string. Okay, so I apply R1. What does R1 do? Well, it switches the first two bits, right? So that's going to give me okay. Now I apply R2. What does R2 do? It switches the second and third bits. Yeah, exactly. It's with, yes, good use of, actually, I can see chat, I guess, because it's coming up in my chat. You switch B1 and B3. So this is going to be what's happening. B1 is just moving along, and all the other bits are staying in the same relative order. So after we've applied all of these, what am I going to get? I'm going to get B1 will have moved to the end. But that's what rotation does, right? That's rotation on that bit string. What was our definition? You take the first element and you rotate it to the end. So it is true that this composition of these rotation toggles gives you the full rotation. Okay, everybody convinced of that? Any questions? Yes, great. Thanks for the thumbs up, John. Okay, so now we're going to continue with the proof of this theorem. Now that we know that we've got the right thing. So the first thing we need to show is that this phi is well defined. What do I mean by that? I mean by that we need to show that if we start with some linear extension, and apply phi to it, then phi of that linear extension is going to end up where it should be, namely a bit string with m plus n bits, n of which are equal to 1. But that's easy, because think about it. So I've got this linear extension, x1 through xmn plus 1. Well, since this is a linear extension of m disjoint union n, this says m of the xi's are in the first chain, and n are xi's in n. So therefore, it's clear that by definition, phi of L has m zeros and n ones. And so it is indeed where we want it to be. Everybody agree that this shows that This is the map, the kind of map we, okay. You next need to show that it's a bijection. And the easiest way to show that is just by creating the inverse. And of course, once you create it, you need to show it's well-defined. And this I'm going to leave as an exercise, again, just to get you comfortable with these kind of arguments. So now we've got phi as a bijection, and now we need the big part, which is to show that phi is equivariant, right? That's our important thing. Well, why is that? Okay, and here's where toggles really shine, where you see why we wanted everything in toggles. What do we need to show? We need to show that if I do rotation and then follow it by phi, that's going to be the same thing as doing phi first and following it by promotion. And I claim it suffices to show that phi, I'm going to call this quasi-commuting, phi quasi-commuting, because, right, it goes to the other side, but then it changes rotation to promotion. It suffices to show that phi quasi-commutes with the toggles. And this is going to be easier to prove because the toggles, right, just they do very local, small things, whereas rotation and promotion are more global and harder to work with. Why does it suffice to show this? Well, and of course, we need to show it for all I. Since then, and let me just set up some notation to make this easier to write out. I'm going to use capital M for m plus n minus 1, so I don't have to keep writing it out. What is phi combined with rotation? Or rotation first? Well, it's phi, and then rotation, remember, is doing these R toggles. But suppose we proved that phi quasi-commutes with an R toggle. What can I do? I can bring this Rn, exactly, Aditya's fingers are doing the right thing. You can bring this Rn past the phi and it becomes an Sn. And now I can play the same trick. I can bring the Sn, yes, Maria is smiling because this is such a cute argument. Right, this becomes Sn minus 1, and now phi is traveling along. And finally, you are going to get to, right, all the S's on the other side and phi here. But remember, this combination of S's, we showed that, or actually that was the definition of promotion. So we just move things along bit by bit. So does everybody agree that if I can show this, I will be done? And now it's going to be, this is easy. This is really easy, except for the fact that you got to break it down into cases, as is so often the case. So to show that phi of Ri of a bit string is the same as Si of phi of that bit string, there are 4 cases. Depending upon what those 2 bits that you're swapping are, right? So there'll be one, you look at the 2 bits that you're swapping, and they can either be 0, 0, 0, 1, 1, 0, or 1, 1. And I think you know me well enough at this point that you know that I'm going to do one of the cases and leave the rest for the exercises. Okay, so let me do the 0, 0 case. It'll be illustrative, and then you'll be able to do the rest, I'm sure. So let's do the case where bi plus 1 is 0, 0. Okay, well, let's first of all look at phi of Ri of B. So remember, Ri is switching the ith and I plus first bits. What's that going to do to this bit string? Nothing, right? The two bits are zeros. If you swap them, they're still zeros. This is just phi of B, right? Switching those bits doesn't do anything, yeah? Okay, so just to give some notation here, let's let phi of B, remember this is some linear extension with, say it's this one. And now remember, bi plus 1 is 0, 0. What does that tell you about xi and xi plus 1? What can we glean from that? They're both in M, exactly, Aditya. And we can tell, say more. These are adjacent bits in B. What does that tell you about xi and x? They're both in the first chain, and what else is true? They're cover. Yes, they can't be swapped, but Robert, I'm going to go in small stages. You're already there. I want to, right? If these are two zeros, one after the other, by the way we substitute things, xi must be, xi plus 1 must be the next thing after xi in the chain. So this implies that xi is in fact covered by xi plus 1. And then it's clear what Robert is saying. If these are a cover in the chain, it's clear I can't switch them and still have a linear extension. So and this is of course happening in the chain M. So therefore, Si of phi of B doesn't change anything. It's got to still be phi of B, since exchanging xi and xi plus 1 is not a linear extension. But now we're done, right? Because phi of Ri of B, we showed up here that that's just phi of B. And here we're saying that that's Si of phi of B. And that's what we wanted, right? Phi quasi-commutes. When you pull it past an Ri, you get an Si, and you're done. Modulo the other three cases, which are similar. Yeah, I see some smiles. That's great. I love this argument. This is really cool. Questions? Any questions? So we've disposed of the first of the two equivalences. The second one is harder. This was the easy one. We'll at least get started on the second one now, and then after the break, we'll finish it. Any questions? It's a good breaking news. Okay, so let's then deal with the other equivalence I want to prove, which is that promotion on L, right? What we were just dealing with. Is actually equivariant with row motion on ideals, not of the disjoint union, but of the product. So somehow we have to get from this poset, this disjoint union poset, to this product poset. And that's going to take a little while. So let me show you what we need here. And we saw some of it already, but we're going to need more. So recall, most of you already know this definition. Young's lattice denoted Y is just all partitions lambda ordered by containment of diagrams, ordered by containment. So here's part of Y, right? We start with the smallest diagram, which is the empty diagram. That's contained in the diagram with one box. And then you have the diagrams with two boxes. Next, we'll have the diagrams with three boxes. So this is the row. A row is just over a row. If I have the hook, then that's over both a row and a column. And this will be covered by just the column. And you will pardon me if I don't write out the full lattice. I don't think I have time. All right, this goes on forever. Okay, so Young's lattice, well-known object, highly studied. So we're going to want to look at these linear extensions in terms of Young's lattice. How do we do that? So here's the crucial thing that will connect the two. Suppose you're given two partitions, one less than or equal to the other in Young's lattice. Okay. I'm going to look at a set which I'm going to call C mu lambda, and this is going to be all the saturated chains from mu to lambda. So C is going to be a chain of the form. So you start at mu, that's your mu zero. Sorry, I shouldn't use mu zero because that looks like an element of mu. I'm going to use superscripts here. So that's a partition mu zero. And then you get a partition, take any partition which covers it. Remember, this was our notation for cover. And then you take a cover of that and you keep doing until you get to some mu n, which is lambda. So just take a bunch of partitions, one after the other, in covers from mu to lambda. Why do I want to do this? Well, because there's a nice bijection here. There is a bijection. Between the linear extensions of the poset lambda over mu to these chains, but from mu to lambda. And again, it's very simple. Suppose I have a linear extension, which is x1 through xn. That gets mapped to a chain where you start at mu zero, of course, that's given to you. And then you've got these covers. And I just need to tell you how to get the intermediate steps of the chain. And it's very simple. The ith element of my chain, my ith partition, is just the one below it. And I have to add a box, right? Because it's a cover, and you just add the box, right? Remember, x1 through xn, these are labels of boxes. Just add that box. Okay, this will become most clear if I do an example. Come on. So this is the example we always look at. the 2, 2 example. So mu is this, lambda is this. And suppose we take the linear extension. Remember, a linear extension can just be viewed as a labeling of the boxes, which forms a standard Young tableau. Let's take this linear extension. What does the corresponding chain look like? Well, we start with this. And now we add boxes in the order given by the linear extension, right? So this 1 here tells me that I add, first thing is as I add a box in the first row, right? What is the 2 telling me? Now I want to add a box in the second row, the beginning of the second row, right? So that would give me this. Now I add the third 3, that box in the where it should be. And then finally the 4th box. At the end of the last row. And now I've gone from this mu to this lambda just by adding the boxes in the order that the linear extension was telling me to add the boxes. Everybody see what's going on here? Any questions? Questions about this? So let's recall how we get from the disjoint union to this linear extensions of a skew tableau. So recall. We already saw that promotion on the linear extensions of my disjoint union poset is the same thing as promotion on the linear extensions of this skew diagram. And remember, the bijection was as follows, right? We have my M element chain here. And I have my N element chain here. And those labelings of this gave you labelings of this diagram. Right? Where this length is N and this length is M. So, right, the things in the first row correspond to the M chain. The things in the second row correspond to the N chain. And because these 2 rows don't share a column, they're independent, which is why it's the same as having a disjoint union. Okay, so this we can work with either of these posets. They are the same. They are the same. So we now want to translate everything into this chain way of thinking about things. So we're going to do that as follows. So we wish to find a corresponding action now on the chains from M to M plus N, M, N. And for this, it'll be convenient to draw the corresponding interval of y. Draw right? Because remember, these chains are in an interval. The interval in y from left to right rather than right. Usually we draw intervals from bottom to top. We're going to do it from left to right for reasons that'll become apparent in a bit. Okay. So let me do a quick example. Again, we're going back to our canonical example where m and n is equal to 2. And then in y, so we want to looking at the interval from 2 to 4 plus 2, 4, 2, right? And this is what it's going to look like, right? So we start off with 2 elements, and now we want to add boxes until we get to the partition that has 4 in the first row and 2 in the second. So notice we only have 2 possibilities at each stage, or at most 2 possibilities. Since this partition 4-2 only has 2 rows, we can either add a box in the first row or we can add a box in the second row. Those are the only possibilities. And maybe one of them won't be available if the row is already filled. So if I add a box to the first row, that'll give me this. If I add a box to the second row, it will give me this. Okay. What can I get from this one? What partitions can I get to? Well, I do the same thing. I can either add it to the first row, or I can add it to the second row. What about here? Well, if I add it to the first row, yeah, well, I get this one that I already had. So I also have to consider adding it to the second row. That will give me this. Now let's look at this one. Can I add anything to the first row here? No, why not? Because remember, my target is 4-2. I already have 4 boxes in that row. I can't add any more. This will get us too many things in the first row. So I can only add something to the first column. Sorry, well, in the second row is how you, I mean, it is in the first column, but think of it as adding it in the first row, second row. Here, however, I can add something to the first row, and that'll give me this. But I can also add something in the second row. That will give me this. Which this is also a cover. And what are my options from this one? There's only one, right? I have everything I need, I can get in the first row. I can only add one element to the second row. And that gets me to my final partition. Everybody see how this was constructed? Great. Okay. So I'm going to be looking at this post set a lot, and it looks like a rectangle. So I'm going to call it R. So R is from now on going to stand for this interval from M to M plus N. And that's going to be my rectangle. Each cover, as I was saying, is either adding a box, to row 1, or row 2. right? That's how that's formed. So therefore, and this is crucial, R can be written, can be drawn in the plane, R squared, so that each of these lambdas is first of all centered at an integer lattice point. And all the covers are going to be translates of the vectors I plus j. Here, I and j is, this is usual, right? I is along the x-axis unit vector, j is along the y-axis. And I'm going to call that vector u for up, or I minus j, which I'm going to call d for down. Okay, so let's go back and see why that's true here. What am I thinking of this? I'm thinking of this as being drawn. Let's put this at the origin, right? These covers, then I'm going to think of this is a down cover, this is an up cover. And they're each, right? So what would this cover go to? I mean, it's actually not a cover. It's, yeah, thinking of a covers from left to right. What would that give us? What integer point for this guy? Well, I'm going 1 unit up and 1 unit left. So that would give this box coordinates minus 1, 1. What about this partition? What would its coordinates be? Now you're going up 1 and to the right 1, which means you get to what? 1, 1, right? Everybody see you're going 1 over and 1 up. And now we keep doing that. What would be the coordinates of this fellow? Too shy to say anything. 0, 2, right? You're back to the x-axis, but now you're 2 units up. This would be coordinates 2, 2. This would be coordinates minus 2, 2, and you just keep going like this. Finally on top. Okay, everybody see how we can write this in this nice framework. Okay, so why is that useful? It's going to be useful because we're now going to be able to interpret. Yes, it is. It is definitely. This is going to be useful, but we're not going to go to weight spaces. What we're going to think about, right? Because what are we looking for? We're going to be looking at chains in this. And now chains aren't going to go from top to bottom. They're going to go from left to right. We're going to be able to now look at chains as lattice paths, right? Using these coordinates. And that is where we're going to get the power that we need to finish this off. So I think that's enough for the first session in the morning. So why don't we take a break and then we will continue from here.
Hey, thanks, Bruce. Let's round of applause for the morning session. And yeah, this is all recorded, so this will all be available to review and everything. And let's take a 15-minute break and come back on the hour. I'm just gonna leave this open. People can go in and out of the Zoom if they want, but I'll just stay here.
Yeah, I'm going to stay here also because I'm scared if I do anything with my whiteboard.
Yeah, I mean you can walk
up.
around, but this will
Yeah, exactly. I'm just
leave
going
the
to leave
board
it
up.
there.
Yeah,
So nothing
yeah,
happens
exactly.
to it.
Right. I'll just cut this part out of the recording when we post the recording.
Exactly.
Yeah. This is such fun stuff.
Yeah, no, this is a really cool proof.
Yeah.
Yeah, this is really cool.
Me and Oliver were trying to think about your conjectures about the homometry for the fences
Oh
yesterday or
yeah.
2 days ago.
Did you have
It's
any
tricky. Yeah, it's funny how much more complicated it gets after two,
Yeah,
like length
yeah.
two, right?
Two is easy, and after that, it
Yeah.
just explodes.
Yeah,
I
no, it
sh-
seems like it. It's like too many cases, and then you can't, keep track of them
right,
all. So,
right. I should mention that Ben Edenbaum sent me. Uh, there are two people who have been working on fences and
oh, cool.
modeling on fences.
Hmm.
So if you're seriously interested in trying to do something, you might give them a buzz.
Oh, good to know. Yeah, just in case
Yeah.
like one of my grad students gets interested or something.
Exactly. Exactly.
So,
No, I'm sure they would be happy
yeah.
to also have uh I mean I don't know that they're actually starting with it yet, although Ben may have mentioned it to them. But
Hmm.
it's Svetlana Poznako Poznanovich
Okay.
and her student Alec Merton.
Oh, cool. Okay.
So I can, in fact, if you like, I can forward you Ben's email about what they're doing.
Yeah, that'd be great, actually.
Yeah, I'll forward it right now to you and
Cool. Just out of curiosity. No, it just didn't, the conjecture intrigued me. Also,
oh
my grad student Kyle is working on like Hessenberg varieties and stuff, and that post set in particular feels like it has a lot of three plus ones. It really doesn't avoid 3+1 at all for so it's like we're working on some questions about sort of when is a quasi-symmetric function, a chromatic quasi-symmetric function symmetric. Um,
exactly.
and that one's like probably very not, but you never know. There might be like an ordering in which it is symmetric, like a ordering of the edges. And so,
Exactly.
more,
And it has so many nice the reason I got interested in this is because of its connections with cluster algebras. This is
interesting.
these things come up they're called Jim Prop came up with them. They're called snake graphs in
Hmm.
his terminology, and they they are used to compute the mutations of cluster algebras on marked surfaces.
Cool.
What happened was Misha Shapiro, who's my colleague here at MSU and who is one of the leading experts on cluster algebras, had a graduate student where he was um, looking at these from a cluster algebra point of view,
Hmm.
and then um, and then I thought, well, these are really nice posets. Why not see whether there's a dynamical algebraic combinatorics has anything to say about them? And that's how that
Yeah,
paper was born.
that's cool.
Yeah, exactly. The other beautiful thing where fences come up is there's this work of um, oh come on, Mourier Genoux and Ovsienko, where they define. So we all know and love these Q analogs of non-negative integers.
Hmm.
So they asked, well, what about rational numbers? Is there a nice way to define a Q analog of a rational number?
Oh
And there
man.
is.
Right.
And it turns out that, of course, this is now going to be a rational function in Q.
Right. I was going to say it's probably a ratio of Q numbers.
It was not exactly a ratio of Q numbers.
Okay.
That doesn't work out so well.
Okay.
But
Okay.
the polynomials that you use for the numerators and denominators are exactly rank generating functions for the distributive lattice of a fence.
Oh wow. Oh, that's wild.
Yes, it's really. I'll send you that paper that I have based
Yeah,
on
I'd be
because
really
they
curious
have
about
they have a
rational Q
conjecture
analogs.
which
That
has
sounds
been.
so cool.
Yeah. So I also did some work on this conjecture,
Cool.
which has been partially proved. It hasn't been proved in full generality, and if it also catches your interest, I'll give you more information about what's currently known and what's not.
Sure. Yeah. No, it's very cool.
Yeah.
I guess, yeah, I guess for rational Q analogs, I guess you want some properties that rational numbers have. Like you want ring
Exactly.
proper field sort of
Right, right,
things.
right.
Yeah, and I guess the ratio of two Q numbers wouldn't do that, would it?
It turns out that the you'd want these rank generating functions for the distributed lattices of
Right.
fences. They have all the nice properties you would
That's
want.
so cool.
Let's see. Where would that be? Okay, I've sent you that paper.
Oh, thank you.
We get started again.
Okay, so it's I forget what time, 11 a.m. Eastern. I have to do a translation. And we have Bruce doing the last lecture, last 45-minute lecture of AlCoVR. So take it away.
Okay, so we've come to the exciting finish. We're going to finish that last equivariance. And as we had stopped at the end of last time, we could now interpret each chain as a lattice path. So now each chain in the chains of this rectangular host set is a lattice path. Lattice. Use small p for lattice paths. It's going to have m plus n steps because it's going to be, you can check with this coordinatization that we got. It's from coordinates minus mm to nn. That takes m plus n steps. And the steps, remember, are these either up or down, right? So each of these is going to be an up or a down step. So let's go back and look at that in the example just to make sure that it's clear what's going on. So, right? So here's a chain. I'm going to just make the edges, right? This is a chain going cover by cover. And now this can be thought of as a lattice path. Starting from here, we go down, up, down, up. Everybody see how you can think of these chains as lattice paths. Okay. Just say whether the cover you're using is going in this direction or that direction. You got to go in one of the two. So now we have to think of how do the toggles work on this lattice path, right? We're going to translate toggles to this. So recall, what do the toggles do ordinarily? So for any poset P, and linear extension, right? We've seen this a number of times this morning. If I do the ith toggle, it either switches elements I plus 1 and I if this is still a linear extension, or it stays the same if it doesn't. You can check that the corresponding thing on the path is exactly what you want. On paths, this looks exactly what you think it might look like. Question, is the up-down thing really, it went off. Could you just say it? My chat went away before I could hear it.
So like the number of standard Young tableau on like 2 rows is Catalan numbers. Is this related to that?
Yes, yes. So the Catalan numbers, you are counting what are called Dick paths, which are things, certain types of up-down paths. So yeah, it's definitely related, very closely related. Other questions? So let's translate this into the path terminology. Well, it's exactly what you'd think. SI of a path is going to be either switch the I plus first and the ith elements of my right steps. And this happens if these two steps can be switched. That is, if they're up, down, or down, up. And otherwise, the path stays invariant. So if these two guys are both up or both down, right, switching them doesn't do anything. Again, let's go back and look at this example. So, before that, let me make So therefore, pro, now viewed on chains, is just pro of a chain is equal to SM plus n minus 1 down to S1 applied to that chain, where S is defined this way. Okay, so let's start an example so that you can see what's going on. So suppose I take that same path that we had before. So, right, we had this was our rectangle, and we were looking at this path that went down, up, down, up. So that's my initial chain. Now I apply S1. S1 looks at the first two steps and says, can we switch them around? And so the first two steps went down and up, so they would become what? Yeah, Aditya is saying it correctly. They would become up, down. You just switch the order in which they occur. You go up first, and then you go down. Everything else stays the same. Now I apply S2. These two steps are both down, so what's going to happen? Nothing. If I switch two down steps, it's still two down steps. They're just the same. Now I apply S3. What's S3 going to do to this down step and this up step? Yeah, Maria sees it. I can see it in her smile. Okay. Right? So this would be promotion of that chain. Everybody see how promotion is working in the chain world. Okay, so we still need to get ideals in there somewhere. Where do the ideals coming from? Let me show you where the ideals are coming from. So think about it. The center of each diamond, I'm thinking of these little squares as diamonds. Each diamond of my rectangle has coordinates which are integral. Right? Let's go back and look at that. Right? Look at my rectangle here. The center here, what are its coordinates? Zero. This center here has coordinates 0, 1. Right? 0, 0, 0, 1, 0, 2. What's the coordinates of the center here? Exactly. Thank you, John, putting up your, right? It's 1 out on the x-axis, 2 up on the y-axis. Everybody see how, right? These things, they have integer coordinates in the vertices, but also in the centers. Okay, so what else did I want to say here? Yes. So partially order these centers. The centers in exactly the same way as you normally do, right? Say ij is going to be smaller than or equal to I prime j prime if it's coordinate wise. Okay. The resulting poset is the poset I want, m cross n. Right? Again, let's go back to this example, right? We have this, our rectangle looked like this, right? And now we put at the center of each square and we order them, it gives us this, which is 2 cross 2. Everybody see how we're getting this poset? But we don't want just the poset, we want ideals in this poset. How are we going to get ideals? And this is the crucial idea. So given one of these, and this is also why we wrote the R in this weird left to right manner. Given a chain in R, there is a corresponding ideal. In the ideals of my M by N poset, and you get this ideal in the simplest possible way. I is just the set of all these IJs, these centers, such that it's below my path, below my chain. Right? The chain is going from left to right, just take everything below it. Okay, let's do an example, make sure that it's clear what's going on here. Suppose I take the path that I was taking before, right? What would be the corresponding, and actually let me do this back on the previous, this will be better. Yeah, let's me do this here. What's the corresponding ideal to this path? The minimum element, exactly, Aditya, right? It would just be, again, using fattened, right? You've got this little diamond here. It would just give me this minimum. Okay, everybody see how we got the ideal here. Now I'm going to do the following stuff. Now that I'm on ideals, I can do ideal toggles, right? Let's do the following ideal toggles. For every pair of consecutive steps in the path, do the ideal toggle for the square that's just above that, right? So let's give names to these guys. Let's call this W, X, Y, and Z. Or you could label these, if you wish, W, X, Y, Z, same thing. Do the toggle in the square above, right? So S1 was looking at these first two guys. Do the toggle in the square above those. So that would be the toggle corresponding to X. Remember how to toggle in this guy, right? We take the complement, these three guys, take their minimums, which would be these two, and then take the ideal generated by, wait a second. You take, something is wrong here. Second here, 1 second. Oh, no. Sorry. It's the toggle. It's not, I was doing row motion. We're not doing row motion. We're only doing toggles. How do I toggle X? I toggle X by either putting it in or taking it out if I can. Can I, X is not in. Can I put it in and still have an ideal? Sure. I get this ideal. Notice, how does that ideal correspond to this lattice path? It's the ideal corresponding to the lattice path. Now let's do the toggle, which is over these, of the square over these two, which would be this square Z. Toggle with Z. Z is this top element here. Can I put that in? No, it's not an ideal. So this leaves it alone. Again, exactly the same. Now toggle with the square above this pair of elements. That would be Y. What happens if I toggle with Y? Can I put Y in? Yes, I can. And notice, what do I get? I get exactly the ideal corresponding to this path. Everybody see what's going on? Yeah, this is so cool. I agree, Maria. This is just amazing.
What is
Toggling with the ideals is giving me exactly what we're doing with the paths. But
uh,
notice, remember the Cameron-van der Vlas theorem. The Cameron-van der Vlas theorem said that you wanted to toggle from the top down, right? We're not toggling top down here. We're toggling from left to right. So this suggests we want a different toggling order to do this kind of thing. So here's where we're headed.
question.
Question, yeah, go ahead.
So when you say square above, what exactly is the square above?
The square above is you take the first square, which is above the path, and which is above the two elements that you're considering in the path. So if when I'm considering these two elements, the first square above is X, right? That's the first square that's above the path, right? When I'm considering these two elements, then the first square above, and again, I'm going from left to right. So I'm doing this column first, this column next.
Okay.
So the next would be this element and so forth and so on, proceeding left to right.
Okay.
Does that make sense, Aditya? Great. Okay. Any other questions before I go on? Okay. So we want to do, so recall from Cameron-van der Vlas, row motion is Txn through Tx1 applied to my ideal. Where x1 through xn is a reverse linear extension. But this example suggests we want to toggle in another direction. So this example. So you can think of this by rows, right? You do the very top of the post at first and the next row and the next row. Now we're going to do this by columns. Suggests we toggle by columns. Columns rather than rows. So this would be for promotion. But this brings up the question, not every post sets that are ranked have a natural row structure, right? Or even post sets that aren't ranked have a natural row structure. Column structure, not so clear. So we're only going to be able to do this for certain post sets. So let me define now the post sets where we're going to be able to do this kind of column toggling. So this is a definition of Stryker and Williams. Jessica Stryker and Nathan Williams. In a paper of 2012. And it says that poset P is rowed and columned. And usually that's going to be abbreviated to just saying it's an RC poset, row and column. If it can be drawn in the plane, such that every cover is a translate of the down and up vectors of either the up vector or the down vector. Or if you want to be a little bit more explicit, that is, if I have a cover X covered by Y, and X has coordinates ij, then Y can have one of two possible coordinates. It's either has coordinates I plus 1, j minus 1, right, up and to the left, or Y has coordinates I plus 1, j plus 1, up and to the right. Okay, so let's look at an example. I mean, we've already seen an example, but let's see that there are other examples sitting out there. Suppose we took the following poset. So if we start at the origin here, then we would go up here to 1, 1, up here to 2, 2, and then finally here to 3, 1. Or we could go the other way. We could go to minus 1, 1, and then this would be 0, 2 at the top. Okay, everybody see that this is a row and column poset. Questions about this example? So some notes about these posets, because we're going to want to just write them in the plane in a certain type of way. By translation, we can assume the following. First of all, that all of the coordinates that we use, they're all integers. Right? And that just means you put it in the plane with one of the elements as an integer, and then because these vectors translate by integers, everything will be an integer. We can do more though. We can assume that the two coordinates will always be congruent mod 2. Right? And that's by, right, put one of these guys at the origin. Then of course they're congruent mod 2 because they're both 0. But then notice, using these vectors, that will then take us to two coordinates which are both odd. So again, of the same parity. Then doing another cover will take them to something which is both even, etc., etc., etc. So using this, we're going to define columns and rows. So define the jth row of an RC poset as R sub j, and it's just going to be all of the ij's that have second coordinate j. So so I can vary, j is fixed. And similarly, the ith row. This is the j through the ith column. So it's going to be all the things where now the first index is fixed and j can vary. So let's go back to our example. Right? So here, this row, everything in this row would have second coordinate 0. So this is R0. Here, everything has second coordinate 1. So this is R1. Here, everything has second coordinate 2. So we have R2. We could also have D2, but we're not going to in this particular example. Somebody got that joke, I hope. Anyway, right? This column, everything has first coordinate 0. Here, everything has first coordinate -1. Everything has first coordinate 1, et cetera, et cetera. Everybody see how we're breaking things up into rows and columns? Good. So one more thing is, by translation, we can also assume that the rows, again, just to make the notation easy, start at R1 and go to R2 up through some RS, and the columns are C1, C2 up through some CT, say. Right, so just translate it around until the first row are all the things which have y coordinate 1, then y coordinate 2, et cetera, and do a similar thing with the columns. Okay, so here's the crucial definition. Sorry for all the definitions, but it's necessary. So we're going to define two products of toggles. Row J, which is going to be the product of all the x's in the jth row, all those toggles. And similarly, kappa I for the columns. Now, there's a problem with making a definition like this. What is that? Toggles don't necessarily commute, right? So how do we, if we put these to get down in a different order, we might get a different element, right? That's bad. I claim, though, in this case, it's not a problem. So note, if P is RC, row and column, think about it. If I take two elements in the same row, can two elements in the same row cover each other? No, clearly not. So no two elements in the same row cover each other. But wait a minute, on your homework, on one of your assignments, we proved that if two elements don't cover each other, what happens to their toggles? They commute. Exactly. Aditya put his pen in the right. This says that the toggles in row J all commute. So their order is immaterial. It doesn't matter which order we put them down in. They all commute together. And similarly, this is well defined. Similarly, kappa I. We don't need to specify an order because they are in fact commuting toggles. Because they don't, no two cover each other. Okay, so now we're finally ready to define what promotion should look like in this setting. So remember, again, by Cameron van der Vlas, row motion was shown to be row 1, row 2 of. So, right, remember, this had to be a reverse linear extension starting from here and going back. So this was the stuff in the highest row, and then the stuff in the next highest row, and then the stuff in the next highest row. That is, or I shouldn't say recall. This is actually something. This follows by the Cameron van der Floss. We can take any linear extension we like. So we'll take this particular linear extension, right? Because these are all the things at the top of the post set, and then everything below them and so forth. So we're just working down the post set. So now we're going to define if P is an RC post set. Then we're going to let promotion, right? So remember, we had promotion before on linear extensions. Now we're defining it on ideals. We're just doing exactly the same thing, except we're doing it by columns. So you do column 1. We could do it the reverse way if we want, but I like thinking left to right. So you do everything, all the toggles in column 1, then you do all the columns in toggle 2, toggles in column 2, etc., until we get to the end. Okay. So we want to relate these two operators. To do so, we're going to need a lemma. So this lemma can be found in a paper of Hoffman and Humphreys. And it says the following. Let G be a group with generators say G1 through Gn. Such that for all I and J, 2 axioms. First of all, they have to be involutions. And second of all, they commute most of the time. Gi, Gj is the same thing as Gj, Gi, as long as the indices are far enough apart. So Gi and Gi plus 1 do not necessarily commute, but Gi and Gi plus 2 or Gi and Gi plus 3, those all commute with each other. Okay. And notice this looks very much like what you get for a Coxeter group. These kind of, there's no braid relation, but just these two. So in that case, if I take any 2 permutations in the symmetric group and look at taking the products of the generators corresponding to these permutations, right? So write down the product of G of sub pi 1, G sub pi n, right? That's going to be some ordering of the G's. Do the same thing for sigma. Those are always conjugate. And remember, we care about conjugate elements of a group because, as we saw last time, they produce equivariance, right? By the actions, the 2 conjugate elements act equivariantly. So that's why we like this. And I'm going to leave this as an exercise.
Excuse me, hi Bruce.
Yes.
Yes, the This lemma goes back to, I think it's Bourbaki's book.
Ah, okay.
On
Yeah,
Lee
this isn't
theory.
a book, so
Right.
this might not be. Can you give me a precise?
I don't remember that. That's the Bourbaki's Lee algebras and Lee group
The
cell
algebra
volume.
book? Yeah. So
Yeah.
I'm not claiming that this is the first.
Yeah, I think so. Yeah.
It's just the one that they cited in the paper.
I like. Yes.
Stryker and Williams, but
Yes, it's
Bucky, the
yeah. There are 3 volumes, but one of them.
texts.
Yeah.
So yeah, thanks so much, Suichi.
Yeah, that's used for the conjugacy of the Coxeter elements.
Right. Yeah. No. I thought when I saw this that this probably wasn't the first time it's been used, because again, it's so closely connected with Coxeter theory
Yes.
that somebody must have looked at this before.
Yeah, sure.
Thank you so much. Thank you so much.
No problem.
Any other questions or comments? Okay, so now we can prove the big theorem of Stryker and Williams, or one of the big theorems in their paper. So and this is definitely due to them. 2012. For any RC poset, these two actions, row motion and pro motion on ideals, they are equivalent. Okay, so let's go through this. First claim, claim A, in 2 parts. First of all, row motion and what I'm going to call row prime, which is going to be taking these row products of toggles with all segregated, so that you do the even ones first and the odd ones next, or you could do it in the other order. These are conjugate. And the same thing with pro motion and pro prime, where I do exactly the same thing with the column toggles. Those are also conjugate. Well, how can we prove they're conjugate? Well, you would like to use the previous result. We'd like to show that previous result here, right? We like to show that these generators satisfy these two identities. Okay. Sorry, my machine is not letting me scroll as nicely as I would like. I'm gonna have to prompt it. Now it's not letting me write. Okay. Oh, geez. It is completely not working. Any suggestions about what to do? Seems to have, I cannot no longer write with it.
Is something going wrong with the whiteboard?
Yeah, it's shut down. It will not let me write on it.
Oh, let me see.
Could it be that it's like too full?
I just wrote
Uh,
on it, so it's letting me write on it. So I was just troubleshooting that. So on the left-hand sidebar, there's all those different tools. I'm sure you've been using them, but
yeah,
if you go
I've
to
been
like your
trying
grade
each
student,
of them. None of them work.
oh, you know what? This happens to me sometimes. Let me see if I can at least save. Let me save this before it goes away. I'm gonna
Should
export
I
this
try
as
and start
PDF.
a new whiteboard then, or?
Not yet. Let me just export it just to make sure it doesn't go
Okay.
away. And export area. Okay, that's good. Sure. Where do I export to? Okay, this says it has been, hang on, let me view the folder so I don't lose it. Okay, I have the whiteboard saved, so now we can experiment with fixing it. And let's see, the whiteboard can only be closed by the host or the person that opened it. Did you open the whiteboard, Bruce?
I did.
Yeah, you can try closing it and opening it again, and
Okay.
hopefully it'll keep what you did, but otherwise you can just sort of continue.
Right. So let's see here. Okay, can I get back the old one then?
Oh my
or
goodness.
not?
Let me see if I can load one. Board. I have export, but not import. How do I load a whiteboard? See, that's why I saved it.
Let me just continue.
Okay, sounds good.
So we're going to prove claim A by using this lemma that is from Bourbaki, right? So we have to show that we're going to, and I'm only going to prove A1, A2 is similar and is going to be on the homework. So what do we need to show? We first of all need to show that Ri rho I squared is the identity. Why is that? Well, it's the same as before, right? Remember, no two elements of the ith row cover each other. So all the toggles commute. So no two elements of row I cover each other. So all commute. So what is rho I squared? Well, remember, by definition, it's the product of all the things in the ith row, their toggles. But they all commute, so we might as well just move them all to so that we're squaring each of them. But they're toggles. Remember the squares of toggles. Okay.
Oh, I tried to load the old whiteboard and it maybe I'll just undo what I did. That doesn't seem to
Yeah,
help.
please.
There we go.
But these are all one. So that finishes that. What about the second one? Well, I need to show that R rho I, rho J equals rho J, rho I, as long as they're far enough apart. Well, wait a minute. Remember, what do the covers look like? Right? They're always of the something in the ith row and then something in the I plus first row. Right? So if I'm taking two things which are not in consecutive rows, do we have any covers? No, we don't, right? Because these are consecutive rows. The next row up will be over here, and that'll be 2 covers down. So all elements of row I commute with those of row J. And that, of course, means that the 2 elements commute, just as before. Okay, so what have we got then? We've got from claim A, right? These 2 guys are conjugate. And our result about conjugates giving us equivariance, we know that rho and I of P is equivariant with rho prime because they're conjugate. And similarly with pro. I'm going to go over a little since we had that snafu. But that's not what we wanted. We want rho and pro to be this equivariant. And that's finished by claim B, which says, actually, they're not just equivariant, they're equal. These are the same map. And this is, I'm going to leave as an exercise. And that'll finish things up. So now we know that rho and pro are equivariant on ideals, but that's not, again, not exactly what we wanted. We wanted that rho on ideals was equivariant with pro on linear extensions. So you need a last theorem, which is that promotion on the ideals of the product is in fact equivariant with promotion on the linear extensions. And I've given you all the tools you need for that. So this is also going to be an exercise. And that completes the proofs. So I want to thank you all for coming and for listening. And I hope you learned something or at least enjoyed it, even if maybe you didn't learn anything new.